All right, everyone, thank you. We're going to get started here for our fourth discovery session, focusing on the MacKimmie Tower and the Hunter Student Commons that we're in. Hopefully there's not a lot of lost people, because I think there was a little mix-up on the event sign-up that didn't specify the exact floor. So the new invite, or the new events page, does state that, but people would have to go to that. Just wanting to make a note that we are recording the sessions. We have cameras at the back, over here and over here in front. This is our session agenda. I'll give a quick welcome, a safety moment, and washroom location. I'll do land acknowledgement. I'll let Alberta Eco Trust introduce themselves in the Retrofit Accelerator program. I'll introduce our Green Building Technology Access Center. I'll introduce the panels, we'll go through the case study presentation, and then we'll open it up for a question and answer with additional panel questions if needed. We'll have a break, and then if you can stay and join us for a tour, we'll do a tour. Once again, I'll start by introducing myself. My name is Dean Jones. I'm a principal investigator and lab supervisor at our Green Building Technology Access Center on St. Campus. So, quick safety moment. Emergency exits, we have one right here. Go back out the doors you came in, straight across. There's stairwell right there. I believe there's another staircase over here, but these are the closest ones to our proximity here. Bathrooms also just straight ahead, and a water fountain. Anything else to say? Good. I'll start by doing a land acknowledgement. We acknowledge the traditional lands and territories of the Indigenous peoples who have lived on these lands and have taken care of them since time immemorial. We make this acknowledgement as an act of reconciliation and gratitude to those whose territory we reside on or are visiting. What became known as the province of Alberta in 1905 is also the traditional and ancestral home to many diverse Indigenous peoples. This includes Treaty 6, Treaty 7, and Treaty 8 nations. The Blackfoot Confederacy, comprising the Siksika, Kainai, and Piikani First Nations, the Cree, Dene, Nakota, Sioux, Saulteaux, and the Métis Nations of Alberta. We are grateful for the traditional knowledge keepers and elders who are still with us today and those who have gone before us. So I'll pass it off to Alberta Eco Trust, Leanne from Alberta Eco Trust.
Hello, my name is Leanne Kamerami. I'm a coach on the Retrofit Accelerator at Alberta Eco Trust. So Alberta Eco Trust is an environmental charity. We've been operating in Alberta for about 30 years. Our focus areas include climate resiliency, emissions reduction, nature-based solutions, and circular economy. We do our work through 4 ways, through grants, impact investing, strategic engagement, and programs and initiatives. So we have 2 buildings initiatives. One is emission neutral building information exchange. So that's an industry-led initiative for sharing resources and information about sustainable buildings. And then we also have the Retrofit Accelerator. So our Retrofit Accelerator is it's our initiative where we work to reduce barriers to building retrofits in Alberta. So from a building owner's perspective, we offer free coaching, so that guides building owners through the retrofit process, and we also support the development of tailored retrofit plans and business cases. So we do that by introducing people to service providers and offering partially funded studies. Within the capacity building side of our program, we work with our ecosystem developers, and we have developed a retrofit vendor network. We've renamed it, it's not the Trade Outlet Network anymore. And then we also do research to identify favorable systemic conditions for retrofit market transformation. We work on barrier mapping, we do market analysis on resources, skills, and training, and we also do public education discovery sessions, such as this one that you're at this evening. And we also share resources and tools from the learnings in the Retrofit Accelerator program on the MBEX resources website and blog. So lastly, before I hand it back to Dean, we'd just like to acknowledge the funders of the Retrofit Accelerator program. It's funded by Natural Resources Canada through their Deep Retrofit Accelerator initiative, and also made possible by RBC's Foundations Tech for Nature program. Now Dean will talk about the GB Tech building.
Leanne? Thank you to those who showed up. Our apologies on if there's a snafu in getting to the location. The event itself had been updated with the actual room and floor number, so my sincere apologies on that. Just like to introduce you to the Green Building Technology Access Center, where we work at SAIC on SAIC campus. But before that, maybe I could have a quick show of hands from the audience, just to get a gauge of kind of the industry representation here. Do we have any building owners in the room? Actual building owners? Awesome. Okay. Consultants, be it engineering, architecture, energy? Awesome. Any trades? Contractor? Okay, yeah, sorry. That would be contractors. Any specifiers, like product supply or suppliers? Okay, awesome. Okay, that's good. Good to actually see some building owners in here, because that's kind of the main target audience for these discovery sessions. All right, so introducing the GBTAC, Green Building Technology Access Center. Our main mission is to prove, implement, and commercialize new building materials, systems, and methods that lead to the construction or retrofit of buildings to be higher efficiency, lower emission, healthier, and more environmentally friendly. We want to collaboratively create and de-risk holistic, high-performance building solutions to address environmental, social, and economic realities. And we also want to develop and provide training and support systems to upskill the residential commercial construction industries. The pictures you see here are some examples of our infrastructure on SAIC campus, where we primarily focus on energy management, renewable energy integration. We have a wall library that focuses on advanced building and material science, and we have an environmental and architectural ecology theme as well. In the sprung structure you see there, we're currently just finalizing some commissioning of a brand new weathering chamber, where we can actually place, say, a wall sample that's about 9 foot by 9 foot and sandwich it in between an interior and an exterior environment, so we can actually monitor the effect both from an environmental indoor condition to exterior condition that has a spray rack for water penetration potentially, UV lights. So that's a nice piece of infrastructure that's taken a long time, that's actually just about to get commissioned to actually testing a sprung envelope. We also have a E72 structural compression testing rack that we're also getting recommissioned within the sprung structure as well to perform more industry-based testing solutions. So our involvement in the DRE project, we kind of having two primary deliverables, one of them being these retrofit discovery sessions, which are free and educational, and networking sessions. Foundational information and data for deep energy retrofits in Part 3 buildings in Alberta. So we are doing our second in-person Calgary session. We have 3 in-person in Calgary, 3 in-person in Edmonton, and 2 online. We did Edmonton in session back in June, focusing on the Edmonton Expo Center. And we've performed 1 online session already. So stay tuned for the future ones. And as you can see, some other future potential discovery session topics that we'll focus on. Another main part of our project deliverable is a market and gap analysis. So that's more of a desktop research, focusing on the training needs identification, building owners, industry professionals, and policymakers. We want to learn from other jurisdictions. We'll do some financial needs assessment. We'll dive into the code and regulatory impacts and barriers. We assess barriers and risks to accelerating retrofit activity in the Alberta market. So let's introduce our panel. First, we have Annie-Claude Lachapelle. Annie-Claude brings over 2 decades of experience in sustainability and technology to her role as energy manager with facilities development at the University of Calgary. She currently leads the operational sustainability team overseeing green building services, energy management, and building technologies. Next, we have Dan. Dan Sudeiko is the sustainability building specialist at the University of Calgary, working in this role for the last 4 years and the sustainability field for over 8 years. Dan specializes in sustainable building design with a focus on carbon emissions reduction, energy efficiency, and climate resilience. Next, we have John Souleles from DIALOG. Did I say that right, John? Awesome. From DIALOG Design. John is a seasoned architect and partner at DIALOG with nearly 3 decades of experience leading transformative projects in the higher education sector. His portfolio includes landmark initiatives such as the University of Calgary's MacKimmie Complex, Hunter Student Commons, and the Veterinary Learning Commons, each exemplifying his commitment to sustainability, placemaking, and cutting-edge design. So with that, I'm going to pass it over to you, C.
Thanks, Dean, and thank you everyone for coming over, and thank you to State and Eco Trust for setting up this event. So I want to give a little bit of context when it comes about MacKimmie Complex, and then we'll talk about the zero carbon building. We'll talk about the project execution and then the performance. So that'll be our agenda for our presentation. So going back to the context. When it first started, it's important to understand institutions like ours, funding for these type of projects, we don't exactly know when it's going to come. We know we have to plan for it, we know we have buildings that need to be addressed, and we go all the way to design, and then we wait for funding, and funding eventually may appear or may not. So that's a little bit the world we live in, just to give the context. When we do this preparation, we use our strategic plan. That's the key document that guides the decision-making of our executive, our leaders, and it also tells our internal teams how they're going to work. So when you do something like a MacKimmie project, you want to have that strategic vision. You want to have your leaders able to talk up and outside about the project, the same way that internal teams are understanding what the project will be about. And so at the time, Ice High was focused, in about 2016 it was released, and it was focused on students, on campus culture, on experience. And the leaders didn't exactly know what we would do. We had 2 empty buildings, the MacKimmie Library Tower and the Library Block. And they knew we had to do something with it. We had space pressures for certain faculties we needed to address. So the way they talked about it, and what I'm sharing today is actually publicly available. This is part of our student reporting, our journal, that talked to our facilities team at the time in 2016, and they were saying it's going to address many challenges as part of one integrated project. So they were seeing the big picture and seeing everybody who would benefit from the project. It would make the best use of 2 existing buildings. It would reduce our operating costs. It would co-locate and centralize student and staff services in the heart of our campus. Okay, so focus on student experience. Alleviate space pressures with the faculties of social work and nursing. Bring the facility condition index on the MacKimmie Tower and Block to nearly 0, right? We wouldn't have any more deferred maintenance on these buildings. And it would be a positive impact to the global, Calgary economy, as well as we hire a lot of people locally. And of course, it would address a number of code issues that we have. So without doing the advanced planning, we knew these items would be tackled with a deep retrofit. So I also went and looked at the financial statement, because it was really hard to get the details of the financials, and everybody has a question. So I took these out from our website. And what we did is in 2016, we started the planning. So we received about $17 million to do the review, the planning, and the design of the MacKimmie Complex. And just 1 year after we started this work, in 2017, we got the great news that we had an additional $270 million to actually do the project. So you can see how the investment went for the years after that. So the total project to date cost in the books that we can see on our website is about $307 million. So what were the real keys to the success of this project? Well, there were 3 main things. We had a strong leadership team who could talk to the needs of the campus, and who could bring people together under one vision and get people excited about the project. It didn't matter really who it was, if it were a dean or if it were a facilities person, everybody was excited about it. And when they looked at the targets and they looked at the metrics and they looked at the beautiful design of the building, they saw the benefit for themselves and for their teams and for everybody on campus. So we definitely had alignment with our strategic plan. So today, well actually since 2023, we have a new strategic plan, which is ahead of tomorrow. And it builds on top of Eyes High. It's the same idea. We focus on our students, on our researchers. We want to be a top research university. And now we also look at the global picture of the impact the university can have. So as we stand today, 10 years later in the tower, in the complex, we can say that it fully aligns with our strategic plan that we have today. And it will continue to do so because it is innovative, it is bold, it uses all the same terms that you find in our strategic plan. Another key factor was the timing, right? You can make the best plans, you can have the best people at the top talking to everyone. If there's no money, there's no money, right? So the timing is also a key factor, which you have some elements of controls in the planning process where you can be ready if funding comes. So that's in our control, and we do that work. But whether or not the money will come, that's out of our control. So timing was really important. And finally, the third thing, I talked about the strong team representing the project, but also the alignment with the strategic plan. So you heard me say that word multiple times, and you're thinking, okay, I know what a strategic plan is by now. This guides all our efforts as well. So everything in the presentation from here aligns with our strategic plan as well. So our institutional commitments include sustainability, under which the climate action plan is. So that's what Dan is going to talk to. He's going to talk to how the MacKimmie Redevelopment Complex aligns with the climate action plan.
Awesome. Thanks so much, Annie-Claude, and great to see everyone here. I really appreciate that context. It's really important, just given the timing of the project and how our sustainability goals aligned with, the context of the project in that time period. So that was in 2016, 2017, 2018. And simultaneously, while all that planning work was being done, we were working on updating our climate action plan. So, obviously on the plan cover, you can see MacKimmie itself. So the design had already been in progress when the climate action plan was being worked on. And for us, it was important to, showcase MacKimmie and use it as, a launching point for the climate action plan and what it means for the university. So within the climate action plan, we have a couple main goals that I'll get into in a second, but it's primarily driven by our carbon neutrality targets. So, at the time, this was in 2019, we had anticipated a 35% reduction by 2025, 50% by 2030, being close to carbon neutral at 2050. So that's our goal, and that still is our goal today. And we're actually on track to achieving that, but lots of work still to be done. So in the climate action plan, there's 4 primary focus areas. The first, including MacKimmie, is new building innovation. So, this was a combination retrofit project, but also a new building project at the same time. So obviously, new building innovation, existing building, energy retrofits. Green power is also tied into this project, but a very separate but very important piece is our district energy system decarbonization. So if you didn't know, the university campus has a district energy system that supplies all heating, cooling, and generates electricity for the campus. It's a cogeneration system that is connected to all buildings on the main campus. So in the end, MacKimmie was going to have its energy supplied by that district energy system. So the decarbonization of that system and inherently the supply of the energy to MacKimmie complex, it's important to plan for that in going into the future and what decarbonization looks like. So put yourself back in 2016, 2017, 2018. We're thinking about planning MacKimmie. Obviously, LEED is a very prominent building standard at the time, but also the Canadian Green Building Council was developing the zero carbon building standard. And so MacKimmie had, again, perfect timing with the CAGBC developing that standard, and we were able to join them in the pilot program. So obviously there's a whole plethora of standards that we could have considered for this building, but energy was going to be a driving focus of it, and it aligned perfectly with the climate action plan with that being released at the same time. So the zero carbon building standard, I'm just going to briefly talk about it, what it is, And then, John's presentation will get more into the technicalities of how we achieved it, and we'll talk about performance afterwards. But the zero carbon building standard defines carbon neutrality or zero carbon building as one that's highly energy efficient, produces energy on site, or procures carbon-free renewable energy in amounts sufficient to offset the annual carbon emissions associated with operations. So obviously with this, there's a couple of caveats as to what is zero carbon, what's carbon neutral. There's many different definitions out there, but this is one that the Canadian Green Building Council was initially looking at. So there's a few specific pieces that were needed to actually achieve this. The first is what we call the zero carbon balance. So that is looking at all of the emissions produced by the building's operations over a period of time, its lifetime. And in this case, it looks at it annually. It looks at how much energy is consumed, and therefore how much emissions it produces, and how much can be balanced from that. So that is either through renewable energy or through carbon offsets or renewable energy credits. The second is efficiency. So there's a number of efficiency metrics that needed to be met, primarily energy use intensity, but also thermal energy demand intensity, or the TEDI metrics. So these were very important, and these govern essentially how efficient the building is. The third is renewable energy. In this case, the zero carbon building standard requires at least 5% of the building's annual energy consumption to be offset by renewable energy. And so that was part of the inherent goals of this building. And then fourth is low carbon materials. So we considered the embodied carbon of the building, and obviously that was a primary driver in the reuse of the tower specifically, but we did look at it for the entire complex. So I'm going to talk just briefly about whole life carbon. When we do new building projects on campus, this is something we consider. Obviously, operations is very important, but we want to understand the entire impact of carbon throughout the entire life of the building. And so we look at the embodied carbon of the building, the carbon that goes into the structure, into the building envelope, that basically doing life cycle assessments on all elements of the building to understand the embodied carbon, and then look at it operationally over time. And so this is actually taken from MacKimmie. I don't have numbers on the left, but you can kind of get the point. And this is over time, so years on the bottom. But essentially, embodied carbon, there's a jump at the beginning, and then there's going to be, amount of operational carbon used over the lifetime of the building. For the MacKimmie complex, about 24% was embodied carbon, and about 76% is operational carbon. As a building gets more efficient, your operational carbon will decrease and your embodied carbon will become more important. So this is something that we're heavily considering in all of our new building projects, and is a primary driver for reducing embodied carbon as well on all of our projects. So where are we at today? We have the High Performance Green Building Program. This did start before MacKimmie, but MacKimmie was a key point in it. For us, we really want to be a leader in high performance buildings, but a lot of that does include, efficiency is important, but having a great building for our students and our occupants to be in is a primary driver as well. So we use LEED, we certify under LEED for all of our new buildings. So MacKimmie was certified under LEED Platinum, as well as a few of our other buildings on campus, the CDC, the Child Development Center, the EEL building, and Matheson Hall most recently was certified LEED Platinum. So with that, I will pass it over to John to take us through MacKimmie.
So as you can tell, there was very few stipulations on the project before we began. A lot, actually, to sort of contend with when we first got the project. And so we were really, really excited, but also terrified with the requirement of being in a sort of a net zero carbon pilot project, shooting for LEED Platinum, correcting all the code evils, embodied carbon, LCA, and all of it. But in addition to being radically sustainable, we also needed to provide a new heart for the campus. This is in the middle of the campus and is actually quite the way you're actually going to define your geolocation on campus and your identity as a student when you first come here. And it also became the notion of needing to be visually and physically porous, because the existing tower, for those of you who went to the University of Calgary before, was a big concrete bunker and not very transparent, and there was a decided effort from a design standpoint to fix that. The idea of multiple experiences, and this was pre-pandemic, the idea of how you negotiate a campus in a fluid way and how students are actually going to react to the campus. And also showcasing innovation. How does the building itself speak to the innovation that it's actually espousing? And how does it reinvigorate a campus identity? And so, no biggie, sure, let's just roll up our sleeves and start. But if we didn't have that ethos and those design constraints to begin with a strong client, there is no way that we would have been able to get to this solution. And so I truly believe that it needed to start with sort of the University of Calgary's real push to begin with. And so you know what this building looked like before in 1967 as it went up, and what became really, really important, we talked about embodied carbon, is the sequestration of carbon in the existing concrete structure. When we took the panels down, nothing in this building was straight. The columns of the building were sort of torquing up and around, and so we had to figure out how to normalize that, but it became really, really important. We really wanted to save the block and the link, but they were at least 3 codes old and deficient in floor-to-floor heights, and we at least recycled all the materials out of it, but we couldn't make it work as an academic building in 2020. And so it started with also understanding the heart of the campus as it relates to a partie diagram, and understanding the landscape itself started to become larger than what it needed to be. Without the block kind of inserting itself into Swan Mall, we had at least a football stadium's worth of land that was completely unbounded. And so by using the massing of the building, we did a couple of things. We started to get solar exposure where we needed it, but also started to create a much more formalized quad. So if the quad at the Taylor Family Digital Library is more open and useful for sort of day-to-day, this is more of a formalized quad that also looks at the administration building. And so we started to put this massing together as part of the heart of the campus. And as Dan eloquently mentioned, we really leaned into the pilot project at the time, and specifically the flexible approach for option 1, because we really wanted to look at specifically thermal energy demand intensity in a heating environment, which was supposed to be less than, at the time, 36. I'm not sure if that's changed in the new.
Still the same.
Still the same. And an EUI of 25% better than, at the time, NECB 2017, which gave us our target of 100. Now, we went a little bit further than that, but that was couched in what we'll call a very, very specific macro and micro climate analysis. Looking at with our partners at Transolar, the climate, you realize that Calgary at the time, and this is 2018, this has changed now, at the time had a 60% annual temperature differential from winter to summer. And on a day-to-day basis, 20 to 30 degrees. That's getting worse. Those extremes are getting worse. And we had to analyze that to understand what the opportunities were as well. The wind patterns specifically, and also the temperature and intensity of the wind, which are what those 3 diagrams represent. Then we looked at the solar potential. We're number 2 in Canada related to the potential of solar access in the country. And so very precious little has been done to sort of leverage that, but we needed to understand exactly from a facade and from a roof horizontal standpoint what we had as an ability to do that, and you'll see some of those. But then we also took a look at this and said, in order to achieve the aggressive targets, and how we get to the target, is you need to do everything passive first, something that doesn't require energy first. And so we needed to look at building massing, orientation, wind, open spaces, solar, daylight access, and natural ventilation all first before we actually utilized any active means on the project whatsoever. And so active means being sort of radiant panels or in-floor heating or underfloor air distribution. And we talked about the Calgary sort of wind reality as well. That includes sort of the discussion about Chinook winds. So we had also needed to sort of zero in pretty quickly on high performance systems. Like in order to get a LEED Platinum, we talked about rainwater reuse, 100% dedicated outdoor air ventilation, radiant heating and cooling, evaporative cooling to leverage as many of the tricks in the book that we could. What also radically is to employ really intentful natural ventilation strategies and a light night flush system, which I'll take you through shortly. And the other thing is to leverage daylight controls. We didn't need to do a double skin facade. You could achieve a similar result with a single skin facade, but there was a very specific reason for that, and that had to do with design, access to light, wellness, and the ability to sort of create a community beacon. And so we'll see a little bit more about that. So we talked about rainwater reuse. We capture all the rainwater in a cistern. We have a cistern available, and we reuse that water for flushing. It's really tragic that we don't actually get, unless we have a major event, we don't get a lot of water. And so you look at this and you look at the laudable goal of wanting to create these cisterns, but a huge majority of the time they're bone dry. And you have to contend with that. There is a lack of water in this province. And when we do get the water, we're getting it in 150 to 250 year events, which is a completely different ballgame than trying to capture it for reuse. Then we talked about evaporative cooling. The 7th floor of this building, as it went up, was the actual original mechanical floor. And it was mid-swing in the 1967, 68, when they went up to about the 7th floor, that they needed a new library and the tower needed to continue. This building was actually structured to go up to 22 stories. So without actually missing a beat, they continued the construction up. And so the 7th floor, hopefully in the tour you'll see that, is a story and a half, and so that was where the old mechanical systems were. The current mechanical systems are now there too, but whereas the whole floor was a mechanical floor before, we now take a quarter of the floor plate with the same systems, and this is where we have ventilation and evaporative cooling. And so evaporative cooling, again, utilizing warm and dry air to come in, being humidified and cooled in one system as a passive measure to sort of be able to provide us some cooling. And the whole of the tower itself was always a dropped ceiling. And immediately we inversed that discussion. So we had a bunch of gymnastics to do at the core of the existing building. We did underfloor air distribution, we removed the ceiling. Very specific reasons for that, not only for an underfloor air distribution system and a low velocity system, but also you'll notice that in the tower all of the concrete is exposed, and the concrete is exposed so that we can actually utilize the concrete for thermal mass, and I'll tell you a little bit more about that shortly. But the displacement ventilation allowed us an ability to sort of ventilate with a low energy system from the floor. And here's some of the discussions we'll go through from a winter condition to a summer condition to a shoulder season. This is clearly a winter condition, minus 30. Why did we use a double skin facade? The double skin facade, you can take, you can take it or leave it as it relates to cost effectiveness. However, what it does for us from a passive standpoint is that when it's minus 30 outside, we were able to model this and actually create a condition with the ability of the two skins to create interstitial space that was always never going to go down lower than 12 degrees C. And what that allowed us to do is that we weren't contending with minus 30, we were now contending with a much more temperate 12 degrees. And so that became really, really important. And in this particular scenario, you have ventilation and you also have radiant panels in the ceiling with the perimeter being heat and only as required. Now take that into the other extreme, 30 degrees outside. This is now normal for Calgary. It's going to be 35, it's going to go to 40, and it's going to get hyper hot in that particular cavity. The other thing that a double skin facade does is that you actually can compartmentalize that. You don't need to open the windows inside and out. And then you can provide your radiant cooling in there. So there is a bit of a buffer and allows you to temper the space before it becomes a problem. But then there's the shoulder seasons, which is why we did the natural ventilation. You have natural ventilation in spring and in fall, and you allow that to happen because when it's 12 to 22 degrees outside, you can keep a pretty normal temperature, and you can create the skin, as you can see today. This opened up in here because we needed the ventilation to happen. It happens in the shoulder seasons. You allow natural ventilation, you can control the temperature without using the active systems in a significant way, and then you can open up and actually let fresh air in, which I'll tell you what happens with that fresh air in the next slide. We were also very fortunate. The existing tower had 2 empty elevator shafts that were, because the tower was intended to go all the way up to 22 stories, we had the ability to take one of those and actually use them for an elevator, and the other one we used for a natural ventilation stack. So the air migrates its way from the facade into the core of the space and then gets drawn up and into a natural stack effect, and it creates a natural ventilation environment. We have a fan up on the roof that can then supplement as needed. So that became really, really important for us to be able to sort of use as a natural ventilation stack strategy. And then at night, when it's 2 a.m., the entire building opens up. All of the windows open up. And what we do is we take the natural diurnal temperature differential of Calgary, when it drops in temperature quite substantially during nighttime, and it allows us to charge up all of the concrete with a cooling ability. And then you have some free cooling to start the following day. And that was the strategy, and that way we could actually minimize even more ability for free cooling, as we'll call it. Now, we didn't just limit that to the tower. We actually took the same learnings and we created what we call the vessels, and you'll see the vessels in the block building itself. There's 3 towers there that actually do very similar functions as it relates to the way natural ventilation comes in, it cools, and then it comes up and you can actually ventilate that. And so you'll take a look at that, and it's a sort of an interesting part where we allow natural ventilation to come in and migrate up and through the vessels. You'll see some structural expressionism, some lighting. Became actually a design feature, but it's actually the lungs of the building as well. So in the tower, we talked about the facade itself. Why does it look the way it looks? We were still able to add 2 floors to the top of the building. And we needed that for program. I'll tell you a little bit more about program, because when we set a target of energy use intensity of 75 in the building, we had about 30% less occupants than we do today. And as you all know, when we do design, it actually, the amount of program usually expands. And so with 30% more, we ended up needing to figure out how the energy use intensity was going to actually figure out. But what we did with the facade itself was we wanted the vestige of the existing structure to show through. And one of the reasons we turned the facade on an angle is to facilitate solar access, but also to allow the existing vestige of the concrete structure to show through. We added 2 floors to the top of this building, and that allowed us to get the taper at the top of the structure. But that ended up being an exercise in optimization. When we did this, we worked with our industry partners out in the industry, and we did essentially a computational design exercise that took the existing facade, and we had a problem. We initially started with making everything equal, but it doesn't work, especially when the 7th floor is a completely different floor-to-floor height than every other floor in the tower. We started with 85 panels in the first exercise, and we were able to use computational design to minimize that to 18 separate panels. And that became a very cost-effective exercise for us to be able to reduce material waste and glazing waste. And in fact, we also needed to contend with the corner. The corner, as we turned in this lovely building and we're trying to do these radii on, it became a problem when, again, the 7th floor has a different cadence than everything else. And so if you'll see what you would see here normally is the angle of the building, and you can look at this on the outside. The angle of the building facade is one angle. When it hits the 7th floor, it goes slightly steeper, and then it picks up the same angle again. What that allowed us to do, it allowed us to normalize the corner and to be able to sort of get the look of the building to be more homogeneous. And so that's where we are today. So you're asking, why did we get to the double skin facade? We talked about this as being a beacon and daylight and access to ventilation. But it also was a finite exercise, facade by facade, look after look of every orientation, to see whether a double glazed unit, a single or a triple glazed unit, and whether the unit was on the outside or the inside. Every condition was modeled to find out what the heating demand and what the cooling demand was for each orientation. And that's how we made the decision. On the tower, our triple glazing argon filled 2 low E coatings is on the outside. So we create a warm jacket. On the lower lying building, the energy model told us that it doesn't make sense to do that we need to reverse the conditions. So the single glazing is on the outside, and the triple glazing is on the inside. And that was through finite modeling, our energy model. So that's literally it. I mean, I'm just gonna share some images with respect to the building, and then we might go into some of the metrics that we found. So 68 to 71. A Brutalist building in 2017 when we did an initial final assessment, and then what it looked like in 2021 before the block and the link were constructed. And so we could talk a little bit about the link and the architecture of the link. I'm going to go through this relatively quickly, but it was also a major campus building that becomes a nexus of viewpoints throughout campus. And so the idea of this whole central area in the link is to be able to geolocate yourself as a student, faculty, and staff to know where you are. Because it was a major thoroughfare for students before. I don't know if you remember, there's a big escalator there. And you'd go up the escalator and then you'd try to find your way into the library. But there's a lot of views. And so those views sort of lended themselves to what we call now the apertures of the building, that start to talk about how the building is sited, and those study areas are quite popular with the students. And it becomes really an interesting meeting point. Then, of course, we talked about essentially what the building looks like today. But also, it's an academic building. This building, not only was the tower increased by about 30% in terms of occupant load during design, after we'd set our targets in place, but the block itself started as a stacked set of academic classrooms only. There was no registrar going into the block, and there was no Hunter hub for entrepreneurial thinking. And so it came out of a very finite review of optimizing structure and what a traditional classroom is versus what it needed to be, which is an active learning classroom, and the densities of those, and how do we optimize the actual structure itself. And so the exercise started from there, related to how we actually laid out a reasonable building with the right depth to allow natural ventilation to occur, and how we went through from there. And of course, there was the solar discussion, and the idea of how we're going to provide PVs not only in the facade but also on the roofs of the building. This was a look at one of the vessels itself, and how it becomes architecture and art at the same time. It's a very popular place to sit. But part of the zero carbon balance was that we were able to put the tower roof PV array on and the block facade array on, and that became the 5% that we needed for LEED. But the entire, you can see the entire block has an armature on it, and we're awaiting the right donor, so please get your checkbooks out for slathering the roof of the tower, or the Hunter Student Commons with PVs, because that will end up going from 5% and getting us to 22% of the energy of the building being generated from photovoltaics. So how did we do? We started with a building from the 1960s and 70s that was 500, an EUI of 500, which is quite large. And we went aggressive on the design target of 75. We had to meet the thermal energy demand intensity of 36, so under 36. And our target was 5% energy, but we're likely going to get just about 25 if we optimize the PVs. And did you want to do this one, or should I?
Well, you go ahead.
Okay, so electricity and heating. Cooling is, oddly enough, not the issue. We're still a heating climate in Calgary, as much as everybody would like to believe otherwise. Electricity, based on modeled and in 2023 what was observed. You can see relatively close to the electricity sort of load. What we ran into with electricity load was the users. So essentially, 30% more users, number one. Number two, everybody comes in with a toaster or a kettle. And that becomes a palpable reality. Users will not operate the building the way you think they're going to operate the building. And given the pressures of any given building, you're putting more people in. I won't even talk to you about our metrics in 2020 and 2021, which was, as you know, the pandemic, which completely skewed all of the results. So Annie-Claude and Dan have had the pleasure of having to restart this project in 2023 to benchmark it appropriately. And they're now starting to fine-tune the building as you go through it, right? And it'll be about 5 years before you get into an optimized result. Heating, again, with that many more occupants in the building and the way it's zoned, we do take some lessons away as it relates to the heating demand of the building itself. The higher density becomes a problem for us. Cooling was not an issue. But in general, the total, we started with an aggressive 75. We thought we were likely going to hit 90. We started with 101 in 2023, and these fine people at the University of Calgary are going to meet that target, I can guarantee you. Especially as it relates to, you can see it starting to creep down, especially as it relates to the decarbonization of the district energy system and all of the efforts that they're going to do in the next little bit, because the building was quite significantly hampered, I'll call it, with a high pressure, high temperature steam system, and now your central system is about to sort of kick into a round of, I won't put words into your mouth, you guys tell me. And so occupants, we talked about occupants and their behavior not necessarily being sort of an accurate reflection of what you think you are going to get with respect to the people in the building. But do you want me to do the next slide as well?
Oh, sure.
Okay, so investment. How much does the building cost? Well, we were extraordinarily lucky. In 2018 and 2019, when we tendered the majority of this building, it was pre-pandemic and pre-escalation. So we came in at approximately $650 to $690 a square foot. In a conventional sense, that was probably 10 to 15% higher than normal buildings of a similar configuration at the time. And then the pandemic hit. We couldn't possibly build this building for less than $1,300, $1,400 a square foot today. That's a whole other ball game related to this. And so it's a palpable reality that we live in. I don't believe that a twofold increase in our, and I'm not talking about a net zero carbon building, I'm talking about a conventional building, academic building, being somewhere in the order of $1,000 to $1,500 a square foot today. And you guys can cross-check me on that. But the good news is that increased amount of investment for the envelope and the PVs and all of the systems and the variety of things that we did, but we decreased the capital outlay for the mechanical systems. We're not using the same amount of capital for the mechanical systems, and we have a lot less of them, believe it or not. A lot more passive systems than active systems. And the capital cost savings on reusing of the existing structure, not only for embodied carbon, but just generally not having to construct the new tower, was massive. And there's a projected 85% reduction in utility costs for the University of Calgary based on the original complex, which was basically leaking like a sieve, right? Or normative construction for the 1960s and 70s, right? And plus benefits to health and wellness, community connectivity, enhanced resiliency to climate change because the building reacts to its own environment. And the University of Calgary is currently targeting a 23-year payback, which seems excessive, but not for a higher education institution. So that's all I got.
Let's thank John and Annie-Claude and Dan again. That was awesome.
So now it's to you guys. Let's open up the floor to some questions. We have some prepared, but I think since you guys are here, it makes more sense for you guys to ask as many questions as you got. So I'll be around. Go ahead.
Matt Grace, doctoral student as of 2 weeks ago. Great presentation, guys. Did you put the same property of glass on each side? And did you model the impact of different VT and solid heat coefficient on different orientations?
You guys, I'll just yell. Okay. Sure. So we modeled every facade differently, and we played with the idea of changing the different solar heat gain coefficients, low E coatings, and a couple of things happened during the process. We found that it wasn't cost effective for us to downgrade the glass in certain facades, so we ended up using the higher spec glass accordingly for the tower, and the higher spec glass accordingly for the block and link. There are different specs of glass for the block and link than they are for the tower. The other thing that we ran into was we had to change the glass mid-swing on the project. Because when we, in our architectural conceit, when we design these things and we change a normal grid pattern of curtain wall and you rotate it, to a specific degree related to the solar discussion and trying to create the idea, the architectural idea, we had to structurally increase the thickness of the back body of the curtain wall, which increased our thermal conductivity. So then we had to up the performance of the glass to compensate. So it went from, this is warts and all, everybody. It went from a North American spec glass to a European spec glass, accordingly, because we had to sort of compensate from a performance standpoint. But the result is that we actually got the results we needed from the facade and the performance. And it is different for the block and the link than it is for the tower. With a single facade, which is really a laminated piece of glass on the inside on the tower, but on the outside in the block and link, that also has a low E coating, which is really interesting. So, we have quite a bit of performance related to glass, and we kind of swept over that glass quite a bit. So we looked at the cost savings, but we found it was negligible based on the volume of glass that we were going to order, and we were getting the economies of scale anyway in that.
That was an excellent response. Thank you. We're always surprised at how seldom the north, south, east, and west facades are considered separately on Norwell's Tower. So I would love to hear that. And thank you for introducing me to this concept of architectural conceit. I didn't know that was such a thing.
There is always architectural conceit. Some less than others.
I'll look out for it.
Thank you. Nice presentation there. My question, so obviously, staff was students are allowed to get into that space, which is, so when you say that you maintain the temperature between 12 degrees and kind of about 50 now in the winter, right? How conducive would that be to somebody there at that time? It's just one of.
So you don't occupy the double skin facade. This is actually an exit stair. So this is not part of the double skin facade system. So nobody is intended to occupy the interstitial space of the double skin facade. Not unless you want to cook in the summertime and freeze in the winter. And there's a variety of reasons for that. Given the amount of operable windows that are with the BAS system opening and closing, and given the surprising size of those windows, you couldn't safely allow public to access the interstitial suite. So these are exit stairwells only.
and they're quite large. You'll see the exit stairwells throughout. Those are different. Those are circulatory stairs only. The double skin facade is off limits.
Thank you. So next question is, so does in a typical winter night or day, is the temperature of that industrial space maintained by any other source of heating or just solar heat generally?
Yep. Just by itself, it's the BAS temperature. So there's about 1,000 sensors in the tower and less so in the block and the link. They measure temperature, humidity, and air and wind pressure. And that goes through an algorithm of the BAS system, and it determines when those windows need to open, when they need to close. And it's even tied to the telemetry of a weather station that's on Taylor Family Digital Library. We also have a weather station on the tower. And then it ties to the telemetry of the airport. And so when you get wildfire, when you get smoke, when you get winds, high winds or storms, it actually, the facade itself learns from those things and actually starts to organize itself accordingly.
Thank you. So not each one of the window opens controlled by the BAS, and then is it some of them for you to allow the air exchange, or all the windows?
All of them are independently operable.
Yeah.
Thank you.
Hi, thanks a lot. Quick question. Do you at the University of Calgary have to hire new staff to run this building originally, or did you have the people on hand to deal with this kind of technology?
Good question.
Yeah, I'll come to the mic. So no, we did not hire new people to run the tower. So we had to educate our staff, and it is a steep learning curve. So we're talking about the BAS. I mean, there's the lighting controls. There's a lot of technology. Even the IT infrastructure in the building, and we use what we call the optic, so passive switches to try to reduce the energy usage as much as possible. So everybody on campus who has to work on the tower got extra training, if you want, but we did not get other staff to run the tower and the complex. We also have, this is something I really enjoyed, the analytics that we put on top of our building automation system, which can inform our staff. So obviously with the amount of sensors the number of sensors we have in our building, we can't have one human just keep track of those all the time. So by building a layer of analytics on top, we have this ability to monitor a larger number of sensors with just fewer people.
Just one follow-up. Are the students or the community interested in that information, or have you been putting that up in storytelling about the building?
Yeah, so the community is interested, researchers are interested, so we were waiting to get somewhat of valid data. So since 2023, 2024, that we now have good data for the building. And we share with research projects, and what we call campus as a learning lab with different students who want to use data to do some research. We also use students during the project, so we know we had one master's student at least who was involved with the project. So it has been used for research as well.
Did the university have to redefine what is comfort in the building? Comfort level specifically on temperature, less heating in the winter and less cooling in the summer?
Yeah, we definitely did. That was part of the occupant education. So it wasn't just education for our maintenance staff, but education for the users and for the occupants and what to expect in the building. There is a wider temperature range that will be implemented, I guess, in the core of the building. You can definitely see it during summertime, during peak seasons. Winter, I find it's maintained fairly well. It doesn't get too cold within the core of the building. It's actually quite comfortable, but definitely during the peaks of the summer hours. And what we're finding we're doing, this is why we employ the night flush during the peak summer hours. So we can cool the building as much as possible during the nighttime, but we're finding hotter temperatures at night during some of these summer hours nowadays. And so it's getting harder and harder to actually, utilize that night flush properly. So we are using it to a certain extent, but in the end, it means a bit of a warmer core for the occupants during those peak summer hours. So it is something that we are working with them on, and part of it is 4x4, and it really does make a difference what part of the tower you're actually located in. So you definitely find the south face and the south portion of the tower if your office or where your work is located on the south part of the building. You will notice it, and it's noticeably multiple degrees warmer on the south part of the building versus the north. So that's part of it as well, is building that in, and building their expectations within the building.
So as a follow-up, have you published the temperatures that would be considered normal in the building and do not call facilities if it's within that range?
Yes, we have. Well, yes.
This is the self-serve.
Pretty much. Yes, we have. It's in our occupants. We have an occupant handbook that we distribute to all occupants. It's also accessible online. And it does show, what sort of to expect, what temperature range to expect within the tower, when, whether it's during the summer, what time of day, that sort of thing. So that is in there. It is a higher range for sure.
It's 18 to 25 degrees.
Yeah.
And don't call us until you're frying an egg on your desktop.
Yeah.
Something like that.
Yeah. And we'll talk about this a bit when we do the tour as well. John alluded to it and mentioned it about how the interior portion of the facade on the tower, we chose to allow it to be operable by occupants within the tower. And it basically came down to an efficiency versus, psychological control factor of working in that space. It's primarily an office building with administration functions, also some faculties, but we wanted to give occupants a sense of control within their space versus just pure efficiency. And they do appreciate that, but there are times of the year where they don't want to be touching the windows and ventilating themselves with 40,
50 degree heat, yeah.
Yeah.
So final follow-up question on that. Have you seen, of course they can use their toasters that pronounce to heat their space. Have you seen an increase in space heaters?
Occasionally, we definitely do find them. And the other irony is, as the building becomes more efficient from a heating and cooling perspective, electricity use has a larger impact. So we are definitely finding that with plug loads and having to manage that. We're not going to police every single space. We just can't do that. But we do talk to the occupants who provide education. They do get the handbook. We can only do so much. But if we do see an extremely large spike in electricity usage at certain times of the year, there are certain hints as to why that's happening.
I just wanted to follow up, you made a good comment about that, our heat waves that are kicking in, that you don't get very low heat anymore. So, yeah.
I will say that the building started its design in 2018 and the parameters changed.
Yeah.
And so in that short period of time, the parameters have changed related to how climate is actually reacting. And so you're going to find that issue exacerbated in the future.
On the same subject of wildfire smoke coming into play, and I guess how does the heating and cooling systems rely in some capacity on the natural ventilation systems, or were they kind of upsized to allow for a smoke event, and how does that sort of interact?
I'll speak to a little, and then John maybe. Yes, they are designed to handle that, so we can close the building up, and provide cooling primarily when that's happening. It does mean it's much more difficult to take advantage of the night flush, and typically we can't. It depends on the state of the wildfire, state of the smoke, what the air quality is, and we have to make that decision. And this is something we're trying to work with right now in our maintenance teams on all buildings on campus. MacKimmie, is impacted a bit more than others because it has a lot of natural ventilation. But we are looking at putting together a wildfire smoke plan for the entire campus writ large for many of our different buildings and how to operationalize them during these smoke events. So for MacKimmie, it does have an impact, right? There's no getting around it. We do, use natural ventilation during the summer months. The good thing is that, we can provide enough cooling. It can get a little bit warm in there. That's just the reality of the space. But it is, it's definitely, you could definitely occupy it comfortably.
Yeah. I think with the future, I think you're seeing even conventional LEED silver buildings under LEED 4.1 and the energy atmosphere credits that are coming up. One of your primary moves is going to be a dedicated outdoor air system. So you're going to be dealing with wildfire smoke in a cutting edge building as well as others, because in order to gain the energy efficiency, the solution is to go back to 1975 and clam everything shut and cool it within an inch of its life and keep the metrics between 20 and 22 degrees with a relative humidity of 35, right? And so I think that's the dilemma, right? How much of it can we actually take on with the building itself? And the other thing is cultural change, I think, is the other issue that we're alluding to here. Essentially, people need, with a wider temperature range, whereas it's the norm in Europe, it's not the norm in North America yet. And I think there's a lot to be said related to that. Just widening the temperature range itself is actually a big deal culturally in North America that we need to sort of contend with. But I don't think that there's going to be much offshoot in the future.
I was just going to ask a question about the constructability and having, I guess, skills, traits, being able to execute on this project, and were there some challenges, and how did you work through that, and how involved was the contractor at front?
So the good news is that we didn't have those conversations. I mean, I think we're really cognizant that we didn't want to do things. We wanted to do some things that were pretty cutting edge, but we didn't want them to be completely unconstructible. One of the reasons we did the computational design exercise, we did it actually with Ferguson Glass and Stuart Olson. And we worked on it literally a year before we actually put the working drawings together, because we needed to make sure that the facade was constructible, cost efficient, and was really going to hold up. We even did sort of a testing of the facade. We built a one-to-one mock-up in Florida and did sort of storm modeling on it. And so those are types of things that you kind of need to do. It lends itself to a specific type of procurement. Design, bid, build, probably not the best idea. Construction management, probably a better idea. IPD, probably even better. When you can create a collaborative contractual structure to begin with, and you have contractor, subtrade, design, architect, client, and everybody under the sun under one umbrella while you're designing, it's a way better approach, because then you can put all on the table what is critical, what's not so critical, and what you can play around with, and you know what your parameters are a lot clearer. You don't have to wait for a shop drawing, right? Which is you're way too far down the line. Does that help?
Yeah, that was actually, I had one other question too about your embodied carbon graph. And I'm just curious, you show the embodied carbon slide in kind of the line, and I'm wondering how much were you able to flatten the line after you did the retrofit? Or do you have that data?
That line is based on the design model for the new building. So obviously, it was flattened compared to before, compared to the original model. It was mentioned that there was about an 85% reduction from the original building. So it's down quite significantly from that. Even over code at the time, it was about 50% reduction in energy consumption. So obviously, over time, we're trying to optimize it and flatten it even more. But I didn't put up the line. That's the design.
Yeah,
that's the model.
I was just saying, I mean, I can see the comparison.
I would say the current consuming line is higher, and we're trying to bring it down.
quick operation question. The interstitial space is off limits, I understand. The windows open quite often, so it gets in a lot of dust. How do you clean them? Or do you not?
Yeah. We told them to clean it every year. Some respect. Yeah.
We're not going to tell anybody about how to clean it, but it really maintains itself. When we toured Germany, there was a variety of buildings. We saw about 15 buildings. Some of them were immaculate in terms of the cleanliness of the interstitial space and the double skin facade. Others were filthy. And it really depends on an operational rigor related to these things.
Yeah, at least from my understanding, we do a lot of maintenance workers in there to, work on sensors, replace, different things. Cleaning, I believe, is part of that program. I couldn't say how often we sent, but I know that we do. So I don't think we'll ever get to dirt like dirty. Like obviously we want to maintain the look of the building and cleanliness of the building. And also, energy is tied to that as well. So it's important for us to at least maintain it somewhat regularly, and we have that. It's also only been open for a couple of years, so it hasn't gotten to the point potentially where it could be really dirty. So hopefully that continues down the line. And that's something we can talk about a bit on the tours as well, is our long-term sort of maintenance plan. And there's a lot of moving parts in the building. How are we going to deal with that long-term? I've got time for a couple more, and maybe I can check and see.
Thank you very much. That was amazing. I was hoping to hear and hear from the architect a little bit. So, question. You have a big portfolio to take care of, a number of buildings that you need to, looking after for the future retrofit, renovation, and everything. And I see, and TSQ obviously has some construction. So, do you use any kind of a special tool or software that analyze your portfolio and say which one, what to do, and when to do it?
So there are many criteria that we look at when we look at our capital renewal. So we do have people who look specifically at the plan for the long term for the university. So they monitor the deferred maintenance, they monitor the new need for new programs for additional students to occupy spaces, new research. So there are so many factors that can dictate kind of where we go next. We don't have an overall tool, but it is something we're working on right now. From an energy perspective, I can say that we monitor daily the energy usage of all our buildings on campus. Technically, we have 80 buildings if you calculate, if you take into account all the little ones, but 50 buildings on main campus, and each building has about 3 meters. So we have Excel spreadsheets for one thing, but we do have the analytics that helps us keep track of all the different buildings and benchmark them. And we continuously, every quarter, look at their performance to reorganize where our priorities are and how we look at upgrading and maintaining our buildings. So there is a lot happening in the background when we choose to go in one direction or the other. And it is a team effort for sure to do that.
Thank you. And next question, I have noticed this building is a LEED Platinum certified. But what is Z-Cabin building you mentioned stages? Is it the ZCD design, or you are planning to get ZCD performance as well?
Good question. Yes, it is design certified. We are looking at getting performance, but we're in the process of determining how that's going to happen. We need, part of it is a commitment, to pay for the renewable energy credits, and I'd say that's a work in progress right now. But it is something we are considering.
Unless there's any other questions, I think we should get to the tour. I think we'll have a quick bio break, maybe talk about coffee or anything like that, grab a quick break, but we should Unless there's any other burning questions, well, there's going to be time for questions on the tour. I guarantee more questions will come to your mind. So I think with that,
We thank our panelists again.